Hello everyone, in this video we will talk about how to identify chiral centers in organic molecules. A carbon atom that is attached to 4 distinctly different groups is considered as chiral because its mirror image is not superimposable. For example, let's say I have a molecule like this. So in this case, I have 4 different substituents: bromine, iodine, hydrogen, and then a methyl group. Therefore, this carbon is considered as a chiral carbon. A chiral center is sometimes also referred as stereocenter, or one also refers it as asymmetric center or asymmetric carbon. It is not necessary that only carbon atom that is attached to 4 different groups are chiral. It could be a heteroatom too. For example, instead of carbon, if I have a silicon atom here with the same substituents, it would still be chiral. But in this video, we are going to talk about only organic molecules whose chiral centers are carbon atoms and not heteroatoms. Now, keep it in mind that all chiral centers are stereocenters, but the reverse is not true. This would become much more clear if I give you one example. Let's say I have a molecule like this: 1, 2, 3, 4, 5, and then let's say I have a phenyl ring on this side, and then a double bond here, and then an OH group here. How many chiral centers are there in this molecule and how many stereocenters are there? We have only one chiral center in this molecule. We have OH, we have a methyl group, and then we have a hidden hydrogen, that is 3, and then we have a CH2 unit here. So we do have 4 distinctly different groups attached to this carbon. Therefore, this carbon is considered as chiral. So that is one stereocenter. How about here? We have another stereocenter because geometrical isomerism is possible here. We have a hydrogen here, we have a hydrogen here. Whenever you have a double bond where on each side you see 2 different substituents, then it is possible to have geometrical isomerism. Therefore, the number of stereocenters here is equal to 2, but the number of chiral carbons is only 1. But how about the total number of stereoisomers? The total number of stereoisomers is 2 to the power n, where n is the number of stereocenters. Therefore, this will be 2 to the power 2. Therefore, the number of stereoisomers in this case will be 4. So, when it comes to chiral carbon, we have only one chiral carbon, but when it comes to stereocenters, we have 2 stereocenters, and that is why all chiral centers are stereocenters, but the reverse is not true. All stereocenters are not chiral centers. So, this distinction is something you should clearly have in your mind. Now, let us look at some examples. Let us say I have a molecule like this. Is this chiral? No, it is not chiral. Why? Because we have a CH3 here, that is a primary carbon, and we have CH3 here, that is also a primary carbon. We have CH2 here, that is a secondary carbon. We have 3 hydrogens on the primary carbons, and then on the secondary carbon we have 2 hydrogens, but we require 4 distinctly different groups, and therefore this is not chiral. How about now? Is it chiral now? No, it is not. So once again, same. Check whether we have 4 different substituents or not. Here we don't have, here we don't have. How about here? We still don't have, because we have a hidden hydrogen, chlorine, and then 2 methyl groups. So we have only 3 different substituents, not 4 different substituents, and therefore this is also not chiral. But how about if I draw a molecule like this, let's say, is this chiral? Yes, we have one chiral center now. This becomes chiral now. Why? Because we have a CH3, we have a chlorine, we have a hidden hydrogen, and then we have CH2Cl. So that is the fourth different unit. It is no longer CH3. Therefore, this carbon atom is indeed chiral. How about, let's say, if I draw a molecule like this, let's say is this chiral? No, it is not chiral. But do we have a stereo center? Yes. Number of stereo centers in this molecule is equal to 1, but number of chiral carbons 0, because we have a double bond. This molecule has a stereo center. Right now we drew the cis isomer. If we put the chlorine down and hydrogen up, then it will become a trans isomer, isn't it? So therefore, the number of chiral carbons, we don't have any chiral carbons. So whenever you see a primary carbon atom, and that is like CH3, it is not chiral. CH2 you can immediately rule out, that is not chiral. Likewise, if you see a double bond, then that is not a chiral carbon, but it could be a stereo center depending upon what substituents you have on both sides. That you need to carefully check. We have one stereo center here. So stereo center is yes in this molecule, but the chiral center is no in this molecule. So let me give another example. So let's say I have a molecule like this. So 1, 2, 3, 4, 5, 6, 7. Let's say I have a phenyl ring here. Let's say I have a methyl group here. Say I have a chlorine here, chlorine here. Identify how many chiral centers are there in this molecule. First, rule out the carbons that are not chiral centers. So we can rule out this. This is also not. This is no. This is also no. And the entire phenyl ring for all 6 carbon atoms, no. So how many carbon atoms are left? We have 3 carbon atoms that are left. So check there whether we have 4 different units or not. Chlorine, that is one different unit, and then we have a hydrogen here hidden, that is another, and then we have a ethyl group, that is the third one, and then CH2, that is the fourth one. Therefore this is a chiral carbon. How about this here? Same, it is also chiral. Chlorine, we have a hidden hydrogen, and then this entire unit we can consider it as one unit, and then this entire unit we can consider as another unit. Therefore this is also chiral carbon. So let me just put a asterisk mark here. Now how about this carbon? Is this chiral? Yes, it is chiral, because we have a hidden hydrogen here, methyl group, and then phenyl ring, and then that is third, and then we have this entire unit. So we have 4 different substituents, and therefore this is also chiral. Therefore the number of chiral centers here is 3. Therefore the number of stereoisomers will be 2 to the power 3. That means we will have 8 isomers, 8 stereoisomers for this molecule. Let's go little tricky examples. How many chiral centers do we have in this molecule? So this is the structure of biotin. Let us first rule out those carbons that are not chiral centers. We can rule out all the CH2s, they are not chiral carbons, and also carbonyl groups we can rule out, they are not chiral carbons. This is also not a chiral carbon. So we have 3 carbon atoms left. Are they chiral? Let us check one by one. We have a hydrogen here, that is 1, and then this entire unit we can consider it as one group, and then we have a sulfur atom, that is the third one, and then here we have a carbon atom and a hydrogen atom, so that is the fourth one. So we have 4 different units, that means this is chiral. But how about this carbon? Is this chiral? It is chiral. Hydrogen, that is 1 unit, and then we have CH on this side. We also have CH here, but this CH is different from this CH. Why? Because for this CH there is a sulfur atom immediately attached to it, but for this CH we have a CH2 on this side, NH on the other side. So therefore we do have 4 different units. Hydrogen atom, that is one different, NH, that is the second different unit, and then we have a CH on this side, that is the third one, and then we have a CH which is attached to sulfur on one side, and then we have a this group. So therefore this carbon atom is indeed chiral. Likewise for this carbon it is chiral. We have hydrogen, we have NH, and then we have CH2, that is the third one, and then we have a CH. Therefore this is also different. So we have 3 different chiral centers in this molecule. How about this example? This will be little tricky. Think about it. First, rule out the ones that are not. We can rule out all the carbons that are in the phenyl ring, and then we can also rule out this one, CH2, carbonyl group, that also we can rule out. We can rule out this, rule out this. How about here? Is this chiral? No, it is not. We have 2 methyl groups, therefore this is not chiral, and the methyl group itself is not chiral, so we can rule out those. How many carbons are left now? 1 here, 2 here, 3 here. Is this chiral? Let us check. Then a hidden hydrogen, that is 2. Then we have a 4-degree carbon, that is third one, and then we have a nitrogen. So that means this carbon atom is chiral. How about this carbon here? We have a hidden hydrogen, we have a sulfur, we have a nitrogen atom, and then we have CH. Therefore this is also chiral. Likewise, let us check this one. We have a hidden hydrogen, and then NH, and then carbonyl group on one side, and then CH here. So therefore this is also chiral. So this molecule also has 3 different chiral centers. Let's draw a couple of more examples. Let's say I have a molecule like this. So let's say I have a structure like this. Let's say, how many chiral centers this molecule has? Rule out the ones first that are not chiral centers. So we can rule out the CH3, all the CH2s, CH3, and then this double bond also we can rule out. So how about this one? Is this chiral carbon or not a chiral carbon? You might think that, oh, we have CH2 here, CH2 here, but then going on the right hand side here is different from going on the left hand side. Why? Because we have CH2 here, but then that CH2 is attached to CH, and then carbon carbon double bond, which is not the same on the left hand side. We have CH2 CH2. So therefore we do have 4 different units attached to this carbon. That means this carbon is chiral. This is the structure of limonene, which you will find it in the citrus fruit peels. How about this structure? Let's say if I draw a molecule like this, how many chiral centers do we have here? Can you find it out? First, rule out the ones that are not. This is not chiral. This CH2 not chiral. This also not chiral. This CH2 also not chiral. Not chiral. Not chiral. This one also not chiral because we have 2 CH3 units. Therefore, this is also not chiral. But how about the other 3 carbons? Let us check this one. We have a hidden hydrogen here, that is 1 unit, and then methyl group, that is second unit, and then we have CH2 on both sides. But then when you look at the next carbon, we have a hydroxyl group on the carbon here, which is not there. Therefore, going on the right hand side is different from going on the left hand side. So that means this carbon is chiral. How about this carbon? Is this chiral? Yes, it is chiral because we have hydroxyl group and then a hidden hydrogen, and then we have carbon and then hidden hydrogen here. So CH, this is CH2, and therefore this is chiral. How about this carbon? Is this chiral? Yes, it is. We have hidden hydrogen, isopropyl group, and then CH2 on the right hand side, CHOH. Therefore, this carbon also chiral. So that means we have 3 chiral centers here. Here we have 1 chiral center. So this means here we will have 2 stereoisomers, and here we will have 2 to the power 3, 8 stereoisomers.